Question 2. Um, this question is about making an aromatic precursor to a valuable antiviral drug on the left. Now, this is a bit of an odd case because we have a trifluoromethyl group here that is not a traditional group that we'll talk about at this point in the course. So I made an assumption here. Just you can assume that it behaves the same way as a methyl group. I want to make it very clear that that is an assumption for the purposes of this course only. That is not always going to be true, and probably not going to be true here if we look at the real papers. But I wasn't trying to complicate things. I just wanted to make this as direct as possible. We're just looking to make this right here using the reactions and the strategies we've put together in this chapter. So let's get on with it. So this is our precursor. Now, this is our final product as far as this is concerned. It's used to make the drug itself later. So how are we going to make this from benzene? So we're going to have to try to put this in place, assuming it behaves like a CH3. That's the Friedel-Crafts acylation. It's the only way we know how to do it. This is a chlorination with iron chloride. Again, only way we know how to do it. And this is coming from a nitration followed by reduction. For the moment, only way we know how to do it. So we have to kind of think then, what do I have in terms of directing ability here that I can work with? Do I have the ability to put these in a very specific way without dealing with an unfavorable mixture of isomers or without getting the wrong isomer, which is useless? So first we want to look at where the directing is here and see whether there's any specific order we have to use. So first, the chlorine is an ortho and para director. Well, it has a group that's para to it, which means it could go in before the nitrogen, since it would direct the nitrogen para. It also has a group that's meta. It's not a meta director at all. So that's going to be a challenge. Either we're going to have to override it, or it's going to send that group to the wrong place. The nitrogen. This also is an ortho and para director, but it's a much stronger one. So again, this one, it has a group that's ortho to it. It has a group that's para to it. So this particular one has everything else directed to where it would send them. So that might be the ideal case to use first. We'll have to think about that. We're going to look at a couple different ways of doing this. This, the acetyl group, is a meta director. Well, we have one group that's meta to it. We have one group that isn't. So we could, hypothetically, do this. We could say, all right, if I started with the nitrogen, and we're going to probably switch out some of the things there, but we'll just say NH2 for now. And then I could basically do the acylation here first. So if I can get to something like this, and again, we may have to change those H's out for something else on the nitrogen, well then basically everything is going to direct the chlorine to here or to here. So we're probably going to get something like this. Now it's not going to be quite this simple, but I'm just showing you the directing part. That this is an ortho direction, this is a para direction, and a meta direction from the trifluoroacetate. Technically, so is this. So we might have an isomer problem there. It depends on what we've done with this nitrogen by the point we actually do this. Okay. So what if I put the chlorine in first? If I did the chlorine first, it is an ortho-para director, so I could then do the nitrogen next. And then I would have the nitrogen. So if I did this, what I'm saying there is I could do this first. And then put the nitrogen in place somehow. And then I have a dual. Both of these are ortho and para directors. But the chlorine is very bad at directing ortho. And it's a different question on this exam about that. So I probably could still manage to selectively get something ortho to the nitrogen. because the chlorine is not going to be very friendly to orthosubstitution. It is too electronegative for that. So that's a possibility as well. So those two possibilities we can work with. All right, so let's see what they actually look like. The first one is putting the amine in first. Well, the only way we really know to do that is nitration, nitric acid, sulfuric acid. We can control how many nitros go in place by temperature, so we'll keep the temp low. We'll get mononitration. This is one of the experiments that you are sadly missing out on with our virtual world. We don't do it to benzene, of course, but we did a nitration. It's a relatively brutal reaction, so it's good to see and experience once in your life. But you know, you'll miss inhaling the fumes, so maybe it's a good thing you didn't do it. Then we're going to have to take this down a bit to the amine. There's a couple different ways to do this. The easiest is hydrogen palladium, or at least the most direct is hydrogen palladium, or other catalyst here. And then reality is we're going to need to cover that nitrogen up a little bit. For the Friedel-Crafts reaction, I can't use the NH2. If I try the Friedel-Crafts reaction with that NH2 there, what I get is something I don't want. That ammonia is basic. So if I put a Lewis acid next to that, what I get is this. This may not be covalent, but I'm going to draw it as such anyway, just to simplify what we're talking about. So I'm going to have a full cation right next to the ring. That's a meta-director. I don't want that. I want my next group here, not next to it. So I have to take care of that, at least for the Friedel-Crafts reaction. So the way that I do that is I temporarily form an amide that I can take back off later as a protecting group. So I can do that with acetic anhydride. I could also do it with acetyl chloride. Doesn't really matter which. Really depends on what I have on the shelf more than anything. Acetic anhydride is a little easier to handle, a little less obnoxious smelling, so preferable if you're going to be working with it. But otherwise, virtually identical. So from there, once I have that nitrogen covered up, I can go a couple of different ways here. One, I could do the chlorination and rely on the size of that group to push things more para. So I can get here. Probably fairly good selection, because that size is going to be enough to make the ortho approach a little difficult. It's not that bad, but you know, para is generally preferable most of the time anyway, so the size will help drive it a little bit more. Okay. The other option is thinking in the opposite way, and that is that the electronics here are going to favor orthosubstitution to some extent. Now, ideally, we'd be able to put something para to the nitrogen, like a sulfonate, and block that and direct to the ortho position and never have a problem with selectivity. The problem is you can't do a Friedel-Crafts with a sulfonate in place. So that directing idea would work for some other reaction. It will not work for a Friedel-Crafts acylation. So I don't have the option to block the para position to the nitrogen. So I'm going to have to take a hit on mixtures here somewhere along the way. It's just a question of where. So let's have a look at this. So if I did the acylation here, it's probably not going to be my major isomer. Because of the size of the acetyl group, I'm probably going to take a yield hit pretty bad here. So this is not necessarily the greatest way to do it. But if I did it that way, well, now everything directs here or here, and again, the size question could be a serious one. So my chlorination is probably a little cleaner here. probably mostly getting chlorination pairs of the nitrogen. And then last step would be just to remove that group, which is basically just base, aqueous base. It's not particularly difficult to remove that. Now, if I had done it the other way here, well, now I've got a kind of trade-off of unpleasantness. What I mean by that is the chlorine is electronegative, which is making this ortho position next to it, not so good. Still technically an ortho director because of resonance, but it's making the ortho position more awkward. The nitrogen doesn't have that problem, but it has the size problem. Now, as it turns out, because of how this reaction works, the steric problem is not as bad. We're actually working outside the plane of the ring, the pi bond breaks, and you're forming something that's sp3, so your approach is not straight line in the plane of the page to that carbon. It's actually from above or below, and so the steric is not as bad. So this is still very reasonable, even though it looks like this group is big and ugly. It's not as bad as it looks. So if I did that and did my Friedel-Crafts then, which is, to remind you, is the azo chloride and aluminum chloride, well, then I'm here. Now I've got what I wanted where I want it. And again, I then just have to take off that same protecting group for the same reason at the very end. If I started with the chlorine first, well, then I would end up nitrating it, reducing it, and protecting it, and I would end up here. So if I started with the chlorine, I'm still going to end up with this structure along the way. So I'm still going to have to put the nitrogen in place. I'm still going to have to reduce it to the amino group. I'm still going to have to cover it up a little bit so that I can do a Friedel-Crafts to put this in place. So at a certain point, the different possibilities are going to converge on really only one way to get it done. That's going to work reasonably well. So there are some questions with this. One, there's not a great way to do this. So if you gave me anything reasonable here, I'm going to give you most, if not all, the points. Two is it's ugly. There's not a clean, perfect way to do it using the reactions that we know. So how is it dealt with industrially? Because this is a marketed drug. It means somebody's got to be able to make it, and preferably fairly cleanly. Otherwise, the cost would be prohibitive and no one would ever buy it. So first and foremost, I've misled you with the question a little bit. And that is, which I mentioned this in the lectures, but I'll say it again here, is no one is ever going to start from benzene. One, it's fairly toxic and unpleasant to handle. And two, because of that, the regulatory costs are enormous. Every step of handling that is very expensive, from shipping it to purifying it to storage to handling to waste. Everything about it is going to take the cost of your operation up. So nobody really wants to use that if they don't have to. So you're really going to start with something that has one or more of the groups in place already. You're going to start with either this, which is aniline, or you're going to start with this, which is chlorobenzene. Or if you're really lucky, you might be able to get this. And then your life is easy. Starting from benzene is a thought experiment. The reality is no one would do that. It's just too difficult and too costly because it's too toxic to handle. Aromatic compounds in general are a little bit questionable sometimes, depending on their structure, but benzene is particularly nasty. So let's have a look at how it's actually done. So here's the original paper. You can tell it's original because it's old, which is kind of offensive to me because I was almost out of graduate school when it came out. So that means if this is old, then I'm a living fossil. What I mean by that in terms of the process is it doesn't even have the name yet. It has a serial number from the company that made it. So it doesn't even have a trade name yet. It's not being marketed at this point. It does not have a a cutesy name to sell to the public in advertising. So that's, you can usually tell you're looking at early parts of the references. When you look at a references or a patent and you see a reference that doesn't contain the name of the compound, it means it's probably very early in the process of making it. So if we scroll down a little bit, you can also tell this is bad PDF scanning circa 1995, because PDFs existed, the internet barely existed, so PDFs that were out there aren't great. And this is an example of one that I pulled down from Science Direct from our library. It's barely readable, but the structures are still intelligible here. So you can see this is the actual drug before it had a name. It was L743-726. And you can sort of see, if we scroll down a little bit, here's our precursor. And if you look to what they started with there, first thing they started with had the chlorine in place and the nitrogen using a slightly different protecting group. Electrophilic substitution, electrophilic aromatic substitution, is a little bit harsh. And I mentioned that in the lectures, that the conditions there are very harsh. So that is not ideal if you're dealing with sensitive compounds. It's also not ideal with certain groups, probably including that trifluoroacetyl group. So this is done in a selective way, because what we had in our version, we didn't have any method of avoiding mixtures. Not great. The way that's done here is a little bit beyond what we talk about in the course, but it's using this nitrogen-oxygen combination here to direct lithiation. By that I mean deprotonation of the aromatic ring to one carbon, ortho to the nitrogen. So it means that after the reaction, what you've put there is only going to be ortho to the nitrogen. And then they did another step to take that group off. So they still had to deal with removing the group just like we did. But the point is, using a little bit different strategy that we haven't talked about yet, you can control the mixture mess that with the electrophilic substitution, we didn't really have a way to do. So this is more advanced, but the idea is that I want you to see here is they're dealing with a similar precursor. So the chlorine and the nitrogen in place. My guess is you could probably buy that. And then they're using different methodology to put the electrophile in place, specifically ortho to that nitrogen. So I was curious about this because it's what I do for a living. So I looked up the actual process version, which is the development of it in a big scale. The previous one is discovery chemistry. You're making milligrams of the compound, just enough to test it, and get very little amounts. If you want to talk about doing clinical trials, you need a lot of material. So at that point, you have to have people come in and move from milligrams up to kilograms. That's process chemistry, process development. So that's what this is. This is another paper that came out like 3 years later. In this case, I should point out, it now has its name. Strangely, it has another compound number, which means, I don't know what that means. They must have developed it with DuPont, because originally it was just Merck, and now it has DuPont, and this says D something on it. So, but the point is, now it has its official drug name, so it's on the market at this point, probably, or on the way to being unmarketed. And if we go down here, look what they started with. They started with a compound that had the chlorine and the nitrogen in place. Again, slightly different protecting group for the nitrogen, and a lot of extraneous details between here and there, but the lithium part is what I was talking about, to make that specific site the only place that gets the trifluoroacetate. So it tells us they probably started with this, but they did have to go through the exact same precursor we're talking about to get to the final drug. Okay, so if I had started with this and then ended up with one step getting to a protected version, they use a T-butyl amide, but there's a reason for that with that particular reaction, but let's just say, R here for the moment. It's not really up to that point. They've saved a lot of steps. They didn't have to do the nitration, which is a very nasty reaction. I don't know anybody that would really want to do that on a ton scale. Chlorination, also not exactly pleasant. So if you can get those pieces already in place, then it's worth buying it. It's worth what it's going to cost you, because you cut out a lot of hazardous material, a lot of waste, and a lot of regulatory oversight, because you're not doing reactions that need to be watched. OSHA doesn't need to watch you if you're not doing the nitration. You know, the EPA doesn't care if you're dumping, you know, well, they do care, but there's grades of hazard. If there's potential release of benzene into the environment, that's a big, big problem, and they're going to be all over your process. If you're not using benzene, you're using something that's less hazardous and a few steps down the line, well then, you know, there's less worry about that. All right, so I wanted you to see how we did it and a little bit of how it's really done. Slightly different, you know, tools advanced, and some of them are a little bit beyond this course, but the concept is exactly the same. They're just using a different set of reactions to keep down the mixture problem. Because if we started from this particular compound, we'd basically have potentially acylation here and here, two different orthodirectors. With what you saw in those papers, it only happens to the site we want, and this is completely eliminated because it's directed. That means kind of like a handoff. So the nitrogen can't hand off things way down here. It can only hand off ortho to itself. So that's why it specifically can only put something directly adjacent. So it beats the mixture problem.